Uh, okay. Yes, yes. Okay, I will explain because the. Okay, I think yeah, right. And before starting the discussion, maybe it's better to explain why you have this kind of unusual session, discussing some particular paper. Even the here, none of the authors are here, but so looks a little bit unfair. But the story is this. Actually, I didn't know this paper until last summer, more precisely 1 month before the Beta Forum on Actions last year. I, I think Andrea was there, right, in Beta Forum, but I couldn't be there because at the time still the COVID situation was not clear enough. But the organizers of Beta Forum kindly allowed me to give a talk by Zoom. And at the same time, actually, just 1 month before the forum starts, the organizers of Beta Forum asked me to study this paper and give a comment because the two of the authors will give a talk at the Beta Forum, and then because the claim of this paper is sort of very surprising because they claim that there is no strong speed problem. So that this is so if they are correct, then maybe many of us lose at least some motivations to be here. But anyway, and then I studied this paper and gave because the organizers asked to give comments, some informally written versions. But unfortunately, because I was not there, I couldn't have enough discussion with the authors of the paper. I had some email exchange with them. Unfortunately, we cannot agree to each other. We cannot arrive at the agreement. Still. Then the last week, Andrea raised up this question again and suggest to have this kind of discussion. So this is why you have this discussion session today. So. Oh, yeah.
They know from this paper, for example, Munich. They are Munich, these models, and also MedTex is, so to say, is still in Munich. And then, of course, the head of the speaker of the MedTex collaboration came to me and said, Andreas, what about this? Is this, you signed for this? And so I published, so is this true? So can I really say? We need to know. Yeah.
So because I think most of you didn't read the paper yet. So basically, I will.
I would say that even if they read the paper, maybe I read the paper.
It's very thick, right? Yes. So I will try to explain, try to summarize their result first. I mean until to the almost the last moment. I don't have an objection with that. I don't have an objection to their result until that point. And at the final stage, I will tell you that in what sense I don't agree with their point in particular stage, which then eventually arrive at the very different conclusions. Of course, I'm in the side of standard. The consideration that accepts the strong speed problems. But okay, so. Okay, for simplicity, I will just consider the QCD with a single quark flavor. I think that's enough to get the whole point. So QCD with single flavor. So then that if you consider the most generic renormalizable QCD Lagrangian with single flavor of quark. Of course, it includes the mass term, left-handed quark and right-handed quark. It's Hermitian conjugate. So the whole discussion, mostly I follow this paper notation also. I try, and then of course we have this famous, theta term. So to be generic, let me consider the complex quark mass, so that you split the quark mass into modulus and the phase. Then apparently, the theory involves two phase angles, alpha and theta. But we know that in the standard textbook, we learned that the one-phase combination, you can eliminate one-phase combination by redefining the quark fields. So that's so you use the U1 axial Spurian transformation. Under which, okay, basically you make the axial phase rotation for the quark field. So beta is some constant. So in opposite directions for left and right field, so it's axial transformation. At the same time, you make this phase transformation to compensate the change of Lagrangian due to this change of the fields. And then we know that because of this famous, ABJ anomaly, in other words, in passing integral approaches, the passing integral measure of the quark field is not invariant under this, transformation, which can be compensated by the shift of zeta parameters. So that we learned that the physics of all observable quantity, for instance, is invariant under this kind of reparameterization of the fields and parameters. So this is also used, this point also has been used by the authors of this paper. But at the same time, you know that there is a parameter, phase combination. More generically, it is like that, which is invariant under this U1 axial Spurian transformations. In this case, just zeta plus alpha. And then we learned that for instance, in particular, if you try to solve the U1 problem, more precisely, try to give some mass to the U1 axial singlet pseudoscalar bosons, non-zero mass, even in the chiral limit, in a way consistent with this Spurian symmetry, or in a way consistent with the Cauchy and Morse identity, then you found that there is CP violation for non-zero value of zeta bar, like eta 2 pi decay or neutron EDM, so on and so on. So that's what you have learned. And that's the famous strong CP problem. For instance, Michael mentioned, briefly touched that this strong CP problem in his talk. So then, in any case, the starting point is that you need to solve the strong CP, U1 problems. In other words, you need to provide extra mass to the eta prime, or in this case, the U1 actual singlet pseudo-Goldstone bosons in the chiral limit. Yeah, one flavor, yes, so that you have one Goldstone boson. So that, for instance, so this is we learned then from Harald Tuft that this U1 problem can be solved by the symmetric breaking. This is explicit breaking, because you need to give the mass to the pseudo-Goldstone boson, so it should be explicit breaking by anomaly and instantons. So somehow the low energy consequence of this explicit U1 breaking by anomaly instantons can be encoded, for instance, this form of the effective interaction, which is usually called the Tuft determinantial interaction of the quark field. For the single flavor case, this is just a sort of instanton-induced mass for the single flavor case. So you parameterize this instanton, maybe at this stage, not necessarily instantons. Just whatever the underlying dynamics is, eventually, in any case, we need the explicit U1 breaking by some Cauchy dynamics. And that explicit breaking also, its consequence should be invariant because this is the feature of the underlying QCD. So invariant under this Spurian Yuan symmetry. So anyway, so suppose that the some underlying QCD dynamics, explicitly anomaly and instantons. But eventually I will discuss instantons, like the authors of this paper, because also it's explicitly in the paper, and I have the same opinion that at the moment, the only explicit calculation, for this piece is the 2-bit calculations. Of course, you have many arguments like based on 1/n expansions or some others or whatever it is, but at least the only explicit calculation to generate for this explicit Yuan breaking based on this symmetric anomaly is the 2-bit calculation, for the instantaneous effect. So the point is that the coefficient mu, the size of this symmetric breaking by anomaly instantons is order in power of the chiral symmetric breaking counting is that 0th order. I mean, that means that this is non-zero even in the chiral limit that m goes to 0. So that's the key point, right? So that if you could have this term generated by the underlying QC dynamics, more explicitly by the instantons, then okay, you can solve the Yuan problem at least potentially, right? But then you found that again this term should be invariant. That's the requirement under this Spurian transformation. Then you found that there are only 2 options, 2 choices. If you require, or if you accept that this effective interaction should be invariant under this Spurian transformation, then you have only 2 possibilities for this phase. I mean, for the entire of my discussion. Okay.
You want it to be invariant in order that the consequent problem will be...
Not necessarily.
No.
Not necessarily. Yeah, that's the point. So one solution is of course, this phase psi is calculable in principle from QCD. And then certainly generically this phase psi would be some function of the alpha and theta, the 2 phase angles in your underlying theory. So then if you require that, this is invariant under this Yuan.
This is why you want it to be invariant.
Oh, that's very crucial thing, and that's what we believe. Also, because in the formulation of QCD, you can explicitly see that, at least for instance, first integral formulation of QCD, you can explicitly show that the whole physical amplitude you computed should be invariant under these transformations. And about that, also this invariance under this Spurian transformation has been also taken by the authors. I also, since many years ago, when I first started the anomaly and all this subject, I learned that this is what I take. So no problem with that. So, but there is another possibility that I wouldn't take. I would throw it out immediately before studying these papers. That was this. That's this solution. Psi minus alpha. So again, if you require that this effective interaction is invariant under this Spurian transformation, we have only 2 choices, this and this. This is standard ones. I would not take this usually because as I told you, this I can consider chiral limit. This is non-vanishing, right? But then you see that why then this complex quantity, which is non-vanishing in the chiral limit, still depend on the phase of the quark mass, right? So that you have a very weird situation that initially you begin with the theory parameters by 1 angle and 1 complex quark mass, and that this phase is just always appear in conjunction with this m magnitude. Now you take the chiral limit, magnitude goes 0. Then naively, I would think that all the phase alpha dependent should disappear in the chiral limit. But here, I mean, if you ignore that point, by some reason, maybe even when you go to the chiral limit, still the physics may still depend on the phase of the m. Then, but still require that this should be a valid symmetry. Then, in principle, you have this possibility. So, about this, I don't have any objection to these authors. So, okay, let's take this possibility. Although, before reading this paper, I would simply throw these options because I need that this is non-zero even in the chiral limit. In the chiral limit, any alpha dependent should disappear. So, okay.
I'm sorry, are they asserting that C is minus alpha?
Sorry?
Do these authors assert that C is minus alpha?
Because C is minus alpha, yes. Yes.
That's their claim.
Yes. Yeah, of course, yes. Then let's calculate this coefficient in dilute instantaneous approximation and to see whether your calculation gives this result or this result.
What is alpha in the current limit? I don't have alpha.
Hmm?
You said in the current limit, what is alpha? Because alpha is defined only when n is zero.
That's true. Yes. So that's with that point, I would simply throw it out this possibility. But the point is that eventually the calculation involves the infinite volume limit. Infinite volume, you begin with the finite volume, also non-zero mass, quark mass, and then you first make the volume to infinity. Then somehow you take this IR cutoff down to 0 by taking the infinite volume limit before the chiral limit. Then you just focus on the final result in the infinite volume limit. Then maybe you are not allowed to quark mass below the IR cutoff, which is taken to be 0 before the chiral limit. So that this is So, but again, every steps in the calculations, you can explicitly see that every step in the calculation, this spurious symmetry is preserved. Then finally, you take the limit, two limit. So you have two parameters, n is the maximal number of allowed winding number of gauge field and space-time volumes. So, you will see that if you first take the infinite space-time volume limit, winding numbers of gauge field. Okay. I will introduce this whole notation later in more explicitly. So the point is that if you first take infinite volume limit before summing over the different values of the winding numbers, then you get this result. But if you take opposite order of taking the limit, first make the summation over the topological sectors up to infinite, not necessarily large enough maximum winding numbers. Then after that, after summing over the topological numbers, then after that take the infinite space volume limit, then you get this result. So this is mathematically true, at least. I will show. So of course at the moment maybe the only way to see which possibility is the correct solution of the QCD, we need some explicit calculation based on in the context of QCD. So that's what these authors tried. And then again, we cannot go beyond the dilute instant gas approximation for explicit computation. So that we'll take that approximation again. Okay. So the strategy is that let's calculate vacuum energy density. In particular, I'm always concerned with the phase dependence, alpha and theta dependence of some physical quantities. So the theta and alpha dependence of the vacuum energy density and the 2-point correlation functions of the quark field. So we'll consider these two quantities. We'll try to calculate the theta and alpha dependence, phase dependence of these two quantities in the context from QCD in the context of the dilute instantaneous gas approximations. But in a sense, I write down to motivate. I introduced this term to provide the non-zero mass to the pseudo-Goldstone boson, eta prime, for instance, even in the chiral limit. Then, this is the kind of effective theory which encode the underlying QCD dynamics which break the U1A symmetry. So then maybe I can try to calculate this quantity, I mean the vacuum energy density and the 2-point functions in the context of this bit phenomenological effective theory. That including this effective theory includes both bare quark mass plus this effective quark mass, which is supposed to be generated by the underlying QCD dynamics, which break U1A explicitly, even in the chiral limit. Okay, so that the calculation of the vacuum energy density and the 2-point function in this bit phenomenological effective theory, including this bare mass and this effective mass together, if you're just interested in the phase dependence, alpha and theta dependence, it's simple. So let me, take this psi at the moment some generic parameter. Okay, then the calculation of the vacuum energy density computed in this effective theory. Again, if you are just interested in the alpha and theta dependence, very straightforward because it's obvious that the alpha and theta, alpha and now the psi dependence just appears through the interference between these two terms. That's the only options. So that the vacuum energy density, you easily if you are focusing on the alpha and the psi dependent piece of the vacuum energy density, okay, then we have this proportional to in any case, that's it. Of course, you could have some high orders. So whatever kind of, for instance, this kind of vacuum energy density may arise through in conjunction with the formation of the quark catechol condensate or the perturbative loops of quark fields. It doesn't matter because in any case, if you consider this alpha and psi dependence, it should arise only through the interference between these two terms, so that this is the possible forms. Also, of course, if you calculate the 2-point functions in the context of this effective theory, then it's straightforward. That's order of n. So the calculation in the effective theory is straightforward. I mean the psi and alpha dependence. But of course, then we should calculate these two quantities from QCD and match your result to this effective theory calculation. Then that will determine the parameter psi in your effective theory. That's the sort of conventional approaches, right? If you have some underlying theory, then you write down the generic effective theory, and then calculate the observable quantity both in the context of underlying theory and effective theory. You match then you can determine the parameters of effective theory in terms of the underlying fundamental parameter. That's the same approach. So now then you calculate vacuum energy density and the two-point correlation functions. Calculation is a bit technically involved. I'm not going to discuss that in detail. Just I write down the result, their result, which I agree. And this is, if you carefully look at the whole steps of calculation, this is basically very similar to the, in some sense, to calculations. So how do you calculate the vacuum energy density? Well, we know that you calculate partition functions. By definition, partition function is the exponential minus omega space-time volume times vacuum energy density. Okay? And then maybe I should, okay, here then. In the passing integral terminology, so let me use the Euclidean passing integral approach to calculate these partition functions. So phi is the, the generic fields of your theory gluons and, single flavor of quarks. Now, then what we are going to use is that classify the possible gauge field configurations in terms of the topological number, winding numbers, nu. So, okay. So you classified, the summation of all possible gauge field configuration, you split into the summation of the topological number nu and the gauge field fluctuations around the, some background gauge field configuration is the definite value of nu. So that nu. So what this means is that somehow this step needs a little bit more of discussion. So that these authors consider at starting point the possible range of nu is from minus n to n. N is some integer, large integer parameters, which parameterize the maximum number of winding numbers in this summation. So mu, what is mu is the integral f dual. I'm not careful about normalization, but you know that with appropriate normalizations, this is the, in certain limit, this is integer valued. So that you consider, summation of the gauge field with particular value of nu first, and then in the later stage, take a summation of all possible value of nu. But here they have, these authors, made some comment which looks very crucial for them. This is the comment, this is the statement in the paper. Let me write actually. I borrowed this statement from their papers. Topological quantization. This means that simply speaking, you assumes that this value of nu is basically integer valued. But this topological quantization of this winding number emerges from the requirement of finite saddle point value of the action in infinite space-time. I think they provide a bit more little bit more detailed discussion on this statement, which I couldn't quite follow. But anyway, this is their statement. So because of this, they claim that the infinite space-time limit, infinite omega is the space-time volume, right? Volume limit should be taken before summing over the topological sectors over integer valued of T. What's the value new? So this is their claim. But what I learned, for instance, from the classical lectures, for instance, the Sidney Coleman's lecture about this discussing the quantization of this winding number, is a little bit different. What I've learned is that you start with the finite space-time. Then you impose boundary condition on the possible gauge field configuration. So you start with the finite, and you start with finite space-time, then impose a boundary condition for the gauge field on the boundary. Of course, this is the large, finite but still large space-time volumes with radius r. Then you impose this boundary condition that okay. On the boundary, let's impose the boundary condition. The gauge field should be pure gauge up to small piece of order of 1 of r squares. Then you easily find that the possible value of nu over this finite space-time is that the integer plus. So this allows that once you impose if you decide that okay, your theory, only the gauge field obeying this boundary condition are allowed, then you get you can classify the all possible gauge configuration or by some integer up to this tiny correction. This small correction doesn't cause any confusions. So, this is what I learned from this Sidney Coleman's lectures. So I thought that this is conventional approaches. Then, okay, then you start with the gauge field and finite space-time volume with this boundary condition. Of course, again, at some stage, you take the R goes to infinity limit at some stage. But at least in these approaches, this statement looks not necessary yet. In some sense, because they have some argument, and for this they say that the infinite volume limit should be taken before summing over the nu. But in this approach, this is not necessarily true. Of course, this approach doesn't tell that still not yet fix the order of the limit. But at least in this approach, I don't see any reason that this should be true. But, okay, this is the one point that I wanted to stress. Okay, now then, let's go to the explicit calculation in these approaches. And this approach, I think, doesn't have any serious conflict with the approaches. Basically, they use the same formula because they in all their calculations they use the omega and n, and then take the limit of infinity in the last stage. But the only concern is that the ordering of these two infinite limits. Then, okay. Now, let me go to these partition functions. Then, I have this partition function. I mean, with this approach, I could split partition function into the contribution from each different topological sector parameters by integer value of mu, integer value of nu, right? Then, okay, they calculated this partition function in particular topological sector in dilute instance case approximation, but they pretend that their calculation, their result may be valid in more general context because they used some argument based on cluster decomposition property and so on, and then they could derive the functional form of this partition function, which is essentially the same as what you would get in dilute instant gas approximation. But I think their argument involves some assumptions, which is essentially, to me, essentially equivalent to the dilute instant gas approximation. So I think in any case, we can simply focus on dilute instant gas approximations, because we don't see that, okay, you have contribution from small instantons, which is reliably calculable, but certainly not the dominant contribution. But we know that this small contribution from dilute instantons or small size instantons is not cancelled by the more dominant contribution from the IR physics. So I think just because we are just interested in the phase dependence, whether whether you have this cosine theta bar or no theta bar dependence, I mean, you can decide just by focusing and looking at the contribution from the dilute gas of instantons. That's the point, because I mean, we are not going to calculate the coefficient precisely. Just we wish to judge which choice of this phase dependence is the correct one. So then this is the result. Up to nu independent and phase independent overall constant, which is totally irrelevant. Nu independent and phase independent overall constant is not of our concern. So up to, I mean, ignoring those kind of overall coefficient, you find that the partition function for given value of nu is given by this. So this is the result, their result. I don't have any objection to this result. So nu, again, nu is the topological, which is supposed to be ignoring the on a small, small piece, integer valued, then, and okay. This is the modified Bessel function of the first kind with index mu, and the variable is the omega is spacetime volume, and eventually you see that this kappa, because the kappa should be has a dimension of energy density, because this should be dimensionless variables. So what this kappa means, at least if you consider the dilute instant gas approximation contribution, then this corresponds to the instanton induced vacuum energy density. Okay, so that this is then dimensionless. So that in a sense, this is just what is that? Integral d for x, part of the what is that? The instanton induced effective terms or vacuum energy density kind of thing. So anyway, this is just the notations. And again, in dilute instant gas approximation, you can show that the so we are also interested in the, I mean, in principle, I think the calculation of the partition function or the calculation of the vacuum energy density should be enough to decide which choice, which solution is the correct ones. But I mean, to make sure things, let me consider this also, 2-point functions. So actually, they spend the length part of their papers to calculate this quantity. again, you can split, this object from, to n, and x prime. So this is the 2-point function computed for the particular class of gauge field configurations having fixed value of nu. Okay? And of course this should be divided by partition functions. So this looks very standard ones, and again, I don't have any objections. I don't see anything wrong with this. Now, this is the explicit calculation. Again, I don't have any problem with this result. But psi. So, for the particular value of the winding numbers, again, you have this phase. By the way, this is again zeta bar, right? The Lie parameterized invariant zeta bar. Then you find that this is a little bit complicated. Again, kappa, the instanton induced vacuum energy density. The kappa is real, and some two-point functions. The point is that this is a new independent of the winding number, and also independent of the phase, divided by mass, basically m. Why this appears in the denominators? Because essentially, this is the basically the matrix element of the propagators, right? So that the inverse of these Dirac operators, but for the complex quark mass, this is essentially related. Basically, this is the matrix element of the inverse of the Dirac operators. Then you know that for the instantons, you have a zero mode of these Dirac operators. So that if this is vanishing, eigenvalue is vanishing, then you have this factor for the left-handed zero mode, 1 over m, right-handed zero mode, 1 over m star like that. So this is the origin of this piece. So basically the contribution from the zero mode of these Dirac operators.
Why does this only get contributions from u equal 1?
Sorry?
Why, I think that instant is this already?
This is basically of course the entire whole space-time you have arbitrary value of nu. But again, as I mentioned, I'm in the dilute instant gas approximation. It's the gas of instanton with single unit winding number and instanton anti-instant is -1 winding numbers. So that's why eventually, if you write down things in some effective local operators, then you have only one phase, exponential I theta or exponential minus, because locally you have either only instanton or n-instantons. Of course, the entire space-time volumes, you could have any value of nu in principle, but so again, this is if you follow up the two calculations, this is the kind of more or less known thing. So that this is the key point is that again I'm interested in the phase dependence and nu dependence, because the question is and also omega dependence, because finally I'm interested in the phase dependence, but here that calculation of the phase involves the infinite omega limit and summation of the nu. So the only thing I need is nu dependence, omega dependence, and phase dependence every step. So I ignore all other details. So then here I have this. minus 1 to kappa omega. So I simply borrowed this result from this paper plus m star b x and x prime. I knew. So you see that at least this result is obviously covariant under the U1 Spurian transformation. So that in every steps you keep this U1 Spurian symmetry. So that for instance you have 1 over m star. They have a common behavior under these U1 Spurian transformations. Okay, then
That's the contribution of a new sector. And that's a contribution from the new minus one.
new. Say again. Sorry.
That's the correlator relative to the new sector.
Yes.
And then you get I new minus one, which is a contribution from a sector that has
But again, because this is why you have this, the reason is that you have m in the denominators. So, but anyway, okay, sorry, as I have stressed it, I'm just focusing on the discrepancy between their result and my viewpoint. So far, no discrepancy. Okay.
In principle, you see on the second term, this is the zero. It's star.
And again, kappa is the induced vacuum energy density. I mean, if you look at this calculation of the partition function, then you sum over the all possible, configuration of the instanton and instanton gas, and then eventually you exponent the summation to get the vacuum energy density, in a sense. So anyway, this is what we know is that okay, instanton induced vacuum energy density it has a dimension 4. You have a scale rho is the instanton size. So, I mean, again, for simplicity, because in any case, I'm interested in just phase dependence, let me focus on the contribution from instantons with some specific size, small enough size, rho. I mean, I'm not going to integrate over the different sizes of instantons, because in any case, they will have the same phase dependence. So, and this law is supposed to be small enough so that this dilute instant gas approximation is a reliable approximation. Then we know that, okay, in any case, this kappa should be mass dimension 4. Also should have the suppression by the quark mass, because we know that in the chiral limit, this goes to 0. And of course, you have this suppression by the semi-classical vector instanton action. And of course, then to have mass dimension 4, this is the only way. Of course, you may have some numbers, very complex numbers that which. Now, to proceed, let me here write down some property of the modified Bessel function that you have learned in the college. That's okay. I knew to y. This is the modified Bessel function of the first kind. Then positive integer and negative integer same. And you can have this expression for the Taylor expansion. I mean, expansion is the y to the k factorial, k plus factorial y, and this is now the very important asymptotic behavior of Bessel functions. So you have two parameters, two variables, integer valued nu and some continuum variable y. So suppose that the what is it? Okay, this integer nu is much bigger than y. In this limit, you know that this modified Bessel function is suppressed by this huge power of, right? Of course, you have these huge suppressions. You know that this is less than 1. If you go to nu large enough, then the huge suppressions for this limit. But you may consider the opposite limit, that the y bigger than square of the mu. Of course, again, let's suppose that this is 1. Then you find that the limiting behavior, asymptotic behavior of this Bessel function is the exponential 2y over y for nu square minus 1 to y plus order of the So here the key feature is that in this limit, you see that the leading term is independent of nu up to this nu dependent piece, which is in this limit, subleading, right? So this is the asymptotic form of the Bessel functions. Now you can use this asymptotic form to calculate the vacuum energy density. Oh, sorry. Oh, maybe I shouldn't erase this, but I hope that this is okay. Then you see that the G and exponential I nu zeta bar is zeta plus alpha, I nu 2 kappa omega is the, again, two limit. For the case that the maximal number winding number n is bigger than omega kappa, in this limit, you see that this partition function, asymptotic form of the partition function is given by this. I mean, you explicitly sum over this and then up to n. But if you consider the opposite limit, omega kappa, again, this spacetime volume times, in a sense, this is instantaneous vacuum energy. Kappa is the vacuum energy density. You multiply the spacetime volumes. That the bigger than maximal value of winding number in this limit. So far, I mean, I didn't, involve, this doesn't involve any physics, just the mathematics, right? The parametric behavior. Then a funny thing is this. We already noted, okay, this is in this limit, this is independent of nu at leading order. Then you have this summation over the zeta bar. This is just what? In the large capital N limit, this is just delta functions, periodic delta functions. So you have exponential E omega. Now, no zeta bar dependent here, because this is nu independent, you factorize out this, and then zeta bar dependent is just what you are left is that's delta zeta bar, delta functions. So 2 times 4 phi omega kappa, 2 pi, I mean this is irrelevant, but anyway, that's it. Of course, 1 plus, you have corrections. So this is the result. Now then, you see that now then you can come back to the question of which order of the limit is the correct one. Of course, if you are in this regime, then normally, you consider large n limit, large omega limit. But what you should compare is actually the quantity, the same dimension. Quantity, the dimension is numbers. So that n and omega kappa, this is the two quantities that you have to compare. In this limit, of course, the correct approach is that, okay, you first make the summation of the nu with infinite range, and then later you take this to infinity. Then you will get in that approach, this will be totally negligible so that you get this result. But if you are in this regime, then okay, then absolutely the correct approach is you first take the limit omega kappa or omega goes to infinity before summing over the nu. Then after that, after taking omega kappa infinity, if you sum over the nu up to infinite n, you have only this result, right? So you give the totally different set of dependence by taking different order of the limit.
Of course, you would say, I mean, in the other case, I mean, this kappa should also depend on the proportion to the quark mass, isn't it?
Depend on.
Quantum energy in the theory should go to zero if the quark mass.
Yeah. Because this is the dilute instant gas calculations. Yes.
Yeah, so this kappa involves an m.
Mm.
So in fact, it's not. It's even so. So it agrees with Lloyd Wheeler and Spielberg. I mean, there's
Oh.
Spielberg, and he has these both limits, and it's essentially what he's always claiming is important as omega, the volume times the mass times the condensate, so to say, something like that.
Okay. So
So it looks very similar.
I didn't try to compare this with the other works. Just I focus on the. Okay. So then then obviously this vacuum energy density is this. What? When the n is much bigger than kappa and minus 2 kappa plus omega minus log delta theta bar. This is very funny things. But of course, it has the same correct dimension, right? Dimension 4, energy density. I mean, they gave a statement on this. I mean, they say, okay, you have this non-analytic behavior. But of course, this is irrelevant if you take omega to infinity. Yeah. So that then now, okay, with this, you go back to the vacuum energy density. You have to calculate the effective theory parameter by the psi. Then, okay, match your result from QCD with the effective theory calculation. Then this is the psi, etc. This is the psi is minus alpha. That's their claim. So far, this is their point. Of course, now eventually the key point is that they insist that this is the correct limit, correct order of the taking the to infinity limit. This is while this is the opposite ordering gives the standard result. Yes. And then you have this with this CP violation, just a standard case. Here you see that those two terms, the bare quark mass and instantaneous quark mass, has a common phase, no relative phase. So physics is totally independent, so no CP violation. It's so obvious. So to make sure, again, you can do the same calculation for the 2-point function of fermions. here is the psi L bar, psi R is the, again, if I use the, sorry, I think I already erased if this is the sum over the contribution from each topological sector, then I already showed that the two-point function for given topological sector has this phase dependence. So bar kappa over m. I mean, this is the good chiral limit because kappa is proportional to m. So that this is regular in the chiral limit, and a some function, and I nu minus 1 to kappa omega plus m star b I nu to kappa omega, sorry. Okay. And I nu. So again, you use this asymptotic behavior of the Bessel functions for two different limits. Again, n is much, much bigger than kappa omega. Okay. And then, you see, then in this limit, to get this, okay, this is the higher order in the quark mass. So this is, you are not interested in this because you are interested in the result in the reading order in the quark mass expansion, so that this is the piece which is zeroth order in quark mass, so that this is the piece non-vanishing in the chiral limit, because kappa over m is no m dependence. So then you have this, here you have nu minus 1, you can write down exponential I nu theta bar is theta plus alpha. You have this 1 over m. This is what? This is m over exponential I nu minus 1 theta bar times exponential I alpha, right? So you move the alpha in front of the summation, and then nu becomes nu minus 1 summation. So then we found that this is cancelled up to with these factors. You ignore this because this is a higher order in m. So in this limit, we found that the two-point function, the phase dependence is essentially, sorry. No, this is the theta, right? Because this exponential I alpha is cancelled by this. So you have this over theta. So that you have, in this limit, you have this phase dependence, A kappa over m plus order of m. Another limit, kappa omega. Well, in this limit, we know that this is independent of this index, nu. I mean, it doesn't matter whether it's a nu or nu minus 1, then precisely this is cancelled. All phase dependence is cancelled because this is mu independent in this limit at leading order. So then what you have is that no phase. You have this only the phase from here. So you see that exponential minus I alpha A so, I mean although they didn't show this limiting behavior, I think until this point, I don't have any objection to the analysis. And the only thing is that the only point is that okay, I mean you can consider two different limits. Then the question is, which limit would be the physically sensible ones? To me, this is obvious, but unfortunately, we cannot arrive at the agreement. The point is this. So now we go back to this n and kappa omega. Well, this is maybe, although I can argue more generically, but maybe to be specific, let me again focus on the dilated instant gas pictures. Then what would be the maximal winding number? So you have this in dilated instant gas pictures, you have K instantons, integer valued, K bar instantons, sorry, anti-instantons, with small size, rho. Then the only constraint you have is that, okay, the total, I mean, in order for this system kind of dilute gas, I mean, you need that this, number of instanton plus number of instanton bounded by omega by the low force, because each instanton has the volume of rho to the force, roughly speaking. So they're putting instantons with the size volume rho to the force in this whole space-time with volume omega. This is the bound. If you consider this range, then of course some order one factor change. But in any case, this tells that the obviously. So to me, because the n is this is the maximum of space-time integral of the gauge invariant operators. So to me, it seems that in any case, the maximum number of winding number should scale as proportional to the omega for given cutoff scale, for given scales. Obviously true for the gas of dilute gas of instantons and instantons. So you are not, to me, it seems that you don't have a freedom to make omega to infinity while keeping this is finite. And then what is the kappa omega? Well, this is omega times, again, to the rho to the first. But now you have suppressions. So again, the first point is that to me it seems that n and omega depend, not independent. Second, both scale as the omega. Now, the another variable, kappa omega, is always suppressed by these small factors. In particular, if you take the rho small enough, for which the dilute instant gas approximation is reliable. So, I mean, in principle, you have a well-defined parametric limit that this is arbitrarily small. I mean, the rho goes to 0. I mean, the acoustic coupling goes to small. Then you can make parametrically this arbitrarily smaller than this. That is my point. But still, the authors somehow reacted that still they think that this n is independent of omega, and so we couldn't arrive at the. Then now with this, it's obvious, right? To me, I mean, because of this, I think this is the sensible limit, right? So the correct order of the limiting is that you first take some of the winding numbers up to infinity winding numbers, then later go to the infinite space volume limit. Then you get the standard result. Okay, that's all. That's all. Yes. Yeah. So again. Only this last discussion of the ordering and the relative magnitude of this and this, except for that, I mean, I fully agree with their result. Yes.
I read this paper long ago, no? And I vaguely remember that they were justifying the order of the limit on the basis of the fact that if you have an infinite volume, different sectors, then you have interference effect that should not be there.
I think that's related with that. I'm not sure which part, because the paper is very, in particular, the supplemented part is very thick. I couldn't follow all the details, but I think that this is what somehow what you are mentioning is somehow related with their statement. I already wrote it. The topological quantization emerges from the requirement of finite saddle point value of actions in infinite space-time. so that the infinite spacetime limit should be taken before summing over the different topological sectors. I think what you are mentioning is somewhat related to this statement.
Probably yes.
But then again, as I mentioned, to me, this seems that this is not necessarily true because I can start with the finite space-time, impose the boundary condition, upward boundary condition. For the gauge field, then I don't have any problem with classifying the gauge field by the integer value nu. And then in the final stage, you take the infinite volume limit, then the whole artifact of your initial this boundary condition, disappears. That's actually Sidney Coleman stated in his lectures. Although I couldn't understand the whole entire details of this, but according to Sidney Coleman, he said that, okay, if you go to the infinite space, you begin with the finite space-time with this non-trivial boundary condition on the gauge field. Then after the calculation, in the last stage, if you take the infinite radius limit, then except for this quantization of the winding numbers, the physics of all other gauge-invariant operators is independent of taking this infinite radius limit. That was his statement. So anyway, I think that's the.
I have a couple of questions. Could you again explain what's the picture in this instance on computation that psi L, psi R has contributions from different winding sectors? So naively, you would say, okay, this gets a contribution from the nu equal 1 sector. So.
Actually, I'm sorry. Maybe I don't. My memory is not at the moment good enough to explain the whole pictures in this because
Well, just counting zero modes.
Of course, diagrammatically, you see, because this is essentially for instance, you have this instanton, for instance. You know that instantons observe the one in this single flavor QCD. Left-handed zero mode and right? Sorry. With this winding number 1, so that you have this, because you have this this index theorem, right? This is precisely kind of things, and then exponential equals 1, then you have this, right? You have this phase. So this is a simple, very simple diagrammatic pictures. But then, for this calculation of partition functions, you should sum up all gas of this object and then finally exponentiate. Then once you exponentiate, then you just focus on the exponent.
What is the diagram on drawing? If a nu greater than 1,
Oh, okay. This is well long. This is just tooth vertex. Nu equals greater than 1. Okay. Of course, the nu greater than, if you have point-like small instantons with nu greater than 1, then of course it will, according to index theorem, you need more the higher power of the perimeter. Yeah. So that's why here I consider the indirect integral approximation. We just focus on the n equals 1 case, the bilinear operators in the exponent of the exponent. So that's why then you have this just gas of the instantons with n equals 1 and arbitrary number n instantons with n equals -1.
But I have another question. It's related to your use of the fixed size instanton.
Okay.
So if you think about a Higgs theory, so let's do SU2 with spontaneous symmetry breaking, then the instanton does have a fixed size.
Of course, you have done this IR cutoff for the instanton size.
Well, the IR cutoff is built in.
Yeah. By the Higgs vacuum values, yes.
By the expectation value.
Yeah.
I don't see where there's any sensitivity to large volume.
Yeah, that's I already pointed out in my talk in this discussion. Yes. Because that's why I can focus on this contribution from the small size instantons, for which the dilated instanton gas approximation is lab enough. Because I don't see any interference between the contribution from the bigger.
This question on the still a bit unsettled by this vacuum energy density there. So with the bottom part, I mean, okay, I understand that if you go to the large volume limit, then you say you can sort of ignore the second term.
You mean this one? This one?
Yeah.
Okay.
I mean, I just try to, if you replace the delta function with some of the usual approximations, and if you think about limits, then I'm not so sure that so just getting a term like this would signal to me that maybe in the derivation before and there is something not really going well, because I don't think it's so trivial to discuss this.
Okay, so at least in their paper, they admitted existing this term. They actually gave some discussion about this term. I have two problems. I mean, first of all, still you may introduce actions. Just you have a serialized dynamical field. Then this is the action potential, right? Very weird action potential. I mean, we know that the potential should be the space-time integral of the potential density. Totally in conflict with these naive pictures. So because of the reason, but again, maybe they may say, I didn't talk with them on this, but if you simply take omega to infinity, so that simply ignore that, then that tells that you don't have an action is precisely massless. Yeah?
But I mean, the delta function itself involves another limit. So I mean, if you want to have some representation of the delta function.
I think I don't have any objection to your viewpoint, but well, they also mentioned that with this term, their result is somewhat consistent with the Barber-Witten argument, which states that this is the minimum at zeta equals to 0 or 2n pi, right? So, but then they say that because you have some non-analytic behavior, so that most of the kind of relations based on the analytic property of the vacuum energy density in zeta equals 0 may not apply. So that's the. So that,
Again, so okay, you would have to go through the derivation and so on.
Yeah.
But I just think that if you did this in a term like this should not appear in the final result.
Yes.
So to summarize, your point is then omega and n are not really independent. And
to me, omega both
well,
n and yeah.
And so the limit you can't really, just to say a summary, right? So you can't really take first the omega goes to infinity limit, keeping n.
I think you can be a little bit more careful. Carefully check. I mean, with this general result, which is valid for any finite value of n, any finite value of kappa omega, then you use this relation, carefully evaluate. Then you can make sure that essentially you get this. No problem. Yeah.
Just a thing to Neutral and Krieger, they derived an equation for the case of NF equal to 1. For this z, for your z nu,
I mean, partition function.
they
Okay.
have derived an exact equation, which is just z nu equal to this formula.
I see. Okay.
And
But I'm not sure if this is exact. No, I don't think.
Saying, okay, they use from the beginning, of course, that z is a Fourier.
But I think they use some sort of dilute instant gas pictures. No? Okay. Let me look.
No. It is.
So say go again. What is the paper?
It's called Spectrum of Dirac Operator and the Role of Winding.
Okay. 92. Okay. Fine. Anyway,
And of course, I have always the discussions with them. So I pointed them to this.
but to me, I think I don't have any problem just focusing on dilute instant pictures because
You have exposed this somehow. But we have also discussed a lot of this kind of. I just wanted to know whether you have taken the limit in the diagonal, right? So what you're saying is that
diagram.
in the diagonal. So
Which diagram?
in the large n, large volume limit, you have diagonal lines, right? You don't have to go along one direction and then to the other. You can go in a mixed direction. And this is your reasoning suggests that there's like a boundary in this plane, right? You have to stay.
I think because sorry, again, I was not initially prepared for this discussion because, I considered this last summer, then forget about that, and suddenly Andrea asked me to have this kind of discussion. So then I tried to recollect my memory, and but I think because now you have this full functions, which is valid for any value of capital N and omega, then whatever way you take this limit to get the result, I think. Then I remember that in any case, maybe diagonal directions or this direction, I think eventually you get the same result. I mean, this one. That was what I remember, yes. But, yes.
Well,
We keep on discussing. I will talk to you.
Okay. Yeah.
about this, are there any other comments or questions? Because as I pointed out, in September 22, there was this paper of Gian Tvali on gravity and viscosity biology. It's a long footnote.
I read that footnote.
Gian is claiming that doing the limit in one way or the other, you get the same result as you should. And we would be all very happy if it is
Okay.
working. And he claims that in the way they take the limit inverted, they neglect some effect. He discussed this shortly, it's a long footnote, but in the dual formulation with the action replaced by a 3-4. But Guillaume will be here the next week. I'm sorry that you
Okay.
will not be here.
Unfortunately, I'm not here. But I think
come back to this point.
because Enrico mentioned that this footnote, yes, I tried to read his footnote, and frankly speaking, I couldn't follow up his point. I couldn't see what he means by this.
That's
But
why we want the speaker here.
and frankly speaking, also I couldn't follow many of his discussion in the papers because it looks very. I mean, he has always his own. He's so much original that he has only his own viewpoint. Yes.
Yeah, but now that we have a better understanding,
I'm just focusing on the quite technical aspect of this calculation, but I think to me this is the point. To me, I think yes.
Thank you very much.
Thank you.
maybe we can ask her to broadcast. So we can follow it.
Okay. Yes. Sure.
Don't forget to leave the microphone. Otherwise,
Oh,
you will leave.
thank you.
I want to talk to you about this or show you this paper because now I understood much more.